Can you believe this amazing pattern is created using mathematics? This twisted shape is called a fractal. And look at this. When we zoom in, it resembles our original pattern. Yet another fractal. Fractals are figures with an infinite amount of detail. They are everywhere, these bright, weird, beautiful shapes called fractals. Nature creates its own fractals. One fern leaf is repeated again and again to form the shape of a whole plant. Even when a woman's hair is braided, we can see fractals appearing. Look how they increase from the tip to her head, every time each braid getting increasingly bigger. Now that you know what fractals are, let's see what they've got to do with exponents, if anything. Hello there, my name is Dumisane. Welcome to this series on exponents. So what do fractals have to do with exponents? Well, let's investigate by creating the fractal we just saw. Let's look at the triangular shape. We will call our first triangle stage 0. As you can see, at stage 0, we have only one triangle for pointing upwards. For our next stage, let's join the midpoints of each side of the big triangle. That's 1, 2, and 3. Let's see what happens. Now there are 3 triangles pointing up. As you can see on our table, at stage 1, now we have 3 triangles. At stage 2, midpoints of each side of the 3 new triangles are joined, and we get 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles. At stage 2, we have now 3 times 3, which gives us 9 triangles. Do you see what pattern we are making? What do you think will happen in stage 3? How many triangles do you think we'll make? If you count this carefully, you should get 27 triangles. And what about stage 4? After this, it gets rather small to draw. So let's look for a pattern to help us predict how many triangles there will be at each stage. At stage 3, we had 27, and we know 27 is 3 times 3 times 3. Stage 4, we had 4 3s, whereby it gave us 81. Now in stage 5, we're going to have actually 5 3s. So how can we do it? We can say 81 multiplied by 3, which will give us 243. So does the number pattern make it clearer? Each time the stage increases by 1, the number of triangles pointing up is multiplied by 3. They become 3 times more. This fractal pattern continues to infinity. We can keep making the triangle 3 times more in our minds. So at the 6th stage, we'll have 3 multiplied by 3, multiplied by 3, multiplied by 3. It will have to be 6 times. That will be the same as, remember in stage 5, we had 243. That means we can multiply that by 3, which will give us 729. Can you use this pattern to predict how many triangles pointing up there will be in stage 9? One way is to multiply 3 by itself 9 times, right? Another way is to multiply 81 by 243. Why can we do that? Well, 3 multiplied by itself 9 times will be the same as 3 times 3 times 3 4 times multiplied by 3 times 3 times 3 times 3 times 3 5 times. Well, from our table, we know that 3 multiplied itself 4 times gives us 81, which means here we can write 81 multiplied by, and from our table again we know that 3 multiplied itself 5 times gives us 243. So that means here we'll have 243. If you multiply the 281 times 243, will give us 19,683. Wow, that is a lot of triangles. It is time to look for a shorter way to write all the repeated multiplication. Let me show you the correct mathematical way. 3 times 3 will give us 3 to the power of 2. 3 times 3 times 3 will be equals to 3 to the power 3. Well, can you carry on? How can you write 3 times 3 times 3 times 3 in a short way, like this? 3 to the power 4. Let us recap. We learned a new notation in this lesson, a short way to write a number multiplied by itself many times. What does the 2 stand for? It is the number that has to be multiplied. And what does the 10 stand for? It tells us how many times the 2 has to multiply itself. This is a much easier way than to write 2 10 times, don't you think? Now, how do we read this? In other words, how do we say this in weights? We say 2 to the power 10. Let's try again. 2 to the power of 10. 2 to the power of 10 is called a power. The 2 and the 10 also have names. The 2 is called the base, and the 10 is called the exponent. What is 2 to the power 10? So what is 2 multiplied by itself 10 times? Let us look at the sequence or row of numbers as they grow. 2 times 2 gives you 4. 4 times 2 gives you 8. 8 times 2 gives you 16. So if we continue multiplying by 2 each time, then the sequence will look like this: 32, 64, 128, 256, 512, and our final answer will be 1024. Could you see the numbers doubled every time? In the beginning, the numbers grew quite slowly, but then towards the end, the numbers got bigger quite quickly. We call this exponential growth. You can use the y to the power x button on your calculator to calculate powers. To find 2 to the power 10, we can press 2, y to the power x, 10, equal sign. That will give us 1024. Right, let us look at another example. Suppose I could fold this piece of paper with thickness of 1/10 of a millimeter 50 times. How thick will the stack of paper be? Do you want to take a guess? Will it be as high as the table? Will it reach the roof? Will it reach the moon? Let me show you on a ruler. If this is a centimeter and there are 10 millimeters in a centimeter, the paper will be 1/10 of a millimeter thick. So the paper will be 1/100th of a centimeter, which is written in decimal form as 0,01. So after one fold, the paper will be 2 times 0,01 centimeters thick. After 2 folds, 2 times 2, or 2 to the power 2 times 0,01 centimeters, which will give us 0,04 centimeters. After 3 folds, it will be 2 times 2 times 2, which is equals to 2 to the power 3 times 0,01 centimeters, and that will be the same as 0,08 centimeters. Now, it has been proved that it is impossible to fold a piece of paper more than 7 times. Try it if you don't believe me. But for the rest of our example, let's imagine we can. After 20 folds, 2 to the power 20 times 0.01 centimeters will be equals to 10,485.76 centimeters, or just over 104 meters. Can you believe it? After 20 folds, the thickness will be more than 100 meters. How about 21 folds? Well, 2 to the power of 21 times 0.01 centimeter will give us 2,097,152 multiplied by 0.01 centimeter, which will give us more than 209 meters. Now let's see, after 30 folds, it will give us 2 to the power of 30 times 0.01 centimeter. That will be more than 107 kilometers. So, if it was possible to fold our original piece of paper 50 times, our piece of paper will stack 1,125,899 kilometers high, which is more than 1,000,000 kilometers. The moon is 384,467 kilometers from the Earth. So our folded paper would go far beyond it. This sounds incredible, but it illustrates how powerful exponential growth can be. We have seen how fractals have a pattern based on exponential growth. We wrote numbers in exponential form, and so that this can help us with calculations. Now, here's your task. Ask your parents if you can wash the dishes each night. Ask them to pay you 2 cents on the first night, 4 cents on the second night, 8 cents on the third night, and continue like this. Use this table to work out what you'll be paid. After a month, you'll be surprised at how much money you can make. Enjoy washing dishes. Salahan Gatle.